Hello everyone, welcome to the neural net section of this course. I will begin this course by discussing how we build a simple neural model, which essentially copies humans' neural networks. I will then cover feed-forward networks and backpropagation, which focuses on how the model updates itself. So this video is all about these theoretical topics. In the next video, I will review an application on Python. So if you want to learn more about these topics, you can take a look at Chapter 10 of An Introduction to Statistical Learning and Chapter 11 of Data Mining for Business Analytics. So this will be a brief introduction. These two books provide a great detail of these topics. Now let's dive in. Okay, let's do a quick review here. Neural networks, also called artificial neural networks, are models for classification and prediction. So the neural network is based on a model of biological activity in the brain, where neurons are interconnected and learn from experience. So neural networks mimic the way humans learn. The learning and memory process of neural networks resemble the properties of human learning and memory. And the main strength of neural networks is their high predictive performance. As this model is based on neurons in our brains, it's a good idea to take a look at a biological neuron. Here's a simplified illustration of biological neuron from Wikipedia. There's a nucleus centered to the neuron. There's also cell body. Dendrites collect the inputs, and impulse, which is a kind of output, is sent along the axon. This is how a neuron works in a human body. So this is even a more simplified version of a neuron. So there are inputs coming from both sides, let's say input x1 and x2, and it's producing an output. So this is how our model is going to work. Let's assume that there's a function here in the nucleus. Let's call it fx. So fx is going to take the input from first and second dendrite, and it's going to produce an output. That's going to be our model. So if fx, which is a function, is just a sum, for example, then y is going to be x1 plus x2. But there is no learning here. I'm going to add learning in a moment, but this is the very basic idea of a neural network. Now let's add some learning here. So I'm going to take a weighted average of the inputs. So v1 is a weight given to x1 and v2 is a weight given to x2. So the function is going to take a weighted average of both inputs and is going to produce an output. Now I'm going to add a bias here, theta1 and theta2, to cope with x is equal to 0, because if x is equal to 0, then it's not going to produce anything. If x1 is 0, it's going to produce theta1. If x2 is 0, then it's going to produce theta2. So this is basically our very first and very basic model, which is called perceptron model. Perceptron model is going to take a weighted average of the inputs, and it's going to add some kind of bias, which is going to be corrected by using a method called backpropagation. So based on the output, the model is going to go back and change this theta in order to produce a better outcome. So there are a lot of financial applications of neural networks. Bankruptcy predictions, currency market trading, and picking stocks are the most commonly used ones. In engineering, autonomous vehicles and driving applications are also using some kind of neural networks. So the most successful application of neural networks have been multi-layer feed-forward networks. These are networks in which there is an input layer consisting of nodes, sometimes called neurons and perceptrons. The red circles are standing for that. So the red circles are input layers. And we are now adding something called hidden layers to our model. So the outputs of nodes in each layer are inputs to the nodes in the next layer. The last layer is called the output layer. So input is going to be collected from here. It's going to go through hidden layer 1, and it's going to go through hidden layer 2, and it's going to produce an output. A feed-forward network is fully connected network with one-way flow and no cycles. When there are 2 or more hidden layers, then that's called deep neural networks. You see a simple neural network on your screen and a deep learning network, which has more than one hidden layer. Now take a look at this numerical example, which is from Data Mining for Business Analytics book. So this table includes information on a tasting score for a certain processed cheese. The two predictors are scores for fat and salt. indicating the relative presence of fat and salt in the particular cheese sample, where 0 is the minimum amount possible in the manufacturing process and 1 is the maximum. The outcome variable is the cheese sample's consumer taste preference, where like or dislike indicate whether the consumer likes the cheese or not. This figure describes an example of a typical neural net that could be used for predicting cheese preference by new customers based on these data. The nodes are numbered in the example from N1 to N6. Nodes N1 and N2 belong to the input layer. Nodes N3 to N5 belong to the hidden layer, and node N6 belongs to the output layer. The values on the connecting arrows are weights, and the weight on the arrow from node I to node J is denoted by Wij. The additional bias parameters denoted by theta serve as an intercept for the output from node J. So the model is going to predict whether the customers are going to like or dislike this cheese based on salt and fat data. Okay, let's start with first record. The first record includes fat input and salt input. So these inputs are 0.2 for fat and 0.9 for salt. For each node, there will be this term, which is a weighted average of the inputs, and the bias term. So I'm not going to use two biases. So this theta is going to represent both biases at the same time. So this term, the weighted average of the inputs, is going to go through a transfer or activation function, which means that I am not going to take just the sum of these variables, but there is going to be a transferred version of this term. So this activation function can take a couple of forms. So it might be either linear, so I might take, for example, 5 times this term. It might be exponential function or logistic function. This is the logistic function which you might remember from logistic regression lecture. So in this example, I'm going to be using logistic or sigmoidal function, meaning that I am going to take that weighted average term and then I'm going to insert this here. So it's going to be e to the power negative es. For every single hidden layer, I'm going to do this thing. For example, N4 is going to take the 0.2 and 0.9 as an input. Using appropriate weights, it's going to calculate an output. And same thing for N3. It's going to take the same inputs, 0.2 and 0.9, and it's going to calculate a different output because the weights are going to be different. And similarly for N5. All of these nodes, N3, N4, N5, are going to calculate different outputs, and these outputs are going to be input for the last node, which is N6. Now I am going to show you how to use input from the input layers and transfer them in node 3. Okay, so this is going to be the node that I am going to show you. This is a simplified version of the previous model. I only took third node. I'm not showing you fourth and fifth nodes, just to simplify the things. So assume that the weight and the biases are estimated by the model as follows. This is the bias, which is negative 0.3. And then these are the weights. So the first weight is going to be 0.01 and the second weight is going to be 0.05. And lastly, I take the inputs. So this model takes the input from the first node here and takes the input from the second node for here and multiply them by the weights, add the bias term, and it's going to be e to the power negative that term. So all of this calculation gives us 0.43. So 0.43 is going to be output of the third node. So we are going to do the same thing for the fourth node and fifth node, and these outputs are going to be the input for the sixth node, which is here. For every single node, we calculated an output. So the third node's output is 0.43, fourth node's output is 0.51, fifth node's output is 0.52. So the numbers in green circles are the outputs of node 3, node 4, and node 5. And these are going to be the inputs for node 6. So the numbers in green boxes are the inputs for node 6. The numbers in red rectangles are the weights, and the number in the blue rectangle is going to be the bias. So node 6 are going to take the green inputs, multiply them by the red weights, and add the blue bias and obtain an output using the transfer or activation function, which is as follows. So first input is multiplied by the first weight, second input is multiplied by the second weight, and the third input is multiplied by the third weight, and we add the bias and we obtain this 0.506, which is the output for node 6. Based on this output, our model is going to decide whether this is like or dislike. Right now we are saying that this is like just because I'm going to be using a cutoff of 0.5. So this is higher than the cutoff, so I classified this output as like. So you might be saying that where did these weights and biases come from? Well, basically these are calculated or predicted by the model. The weights theta and w are typically initialized to random values in the range from negative 0.005 to positive 0.005. And these initial weights are used in the first round of training. They are updated by means of backpropagation, which I'm going to cover in a moment. So training the model means estimating theta and w that leads to the best predictive result. Okay, now let's review how the model updates itself. So the goal of neural net is to find weights that yield the best predictions. So the process that I described a moment ago is repeated for all records, and the prediction is compared to actual at each record, and we calculate the error. And then error is propagated back and distributed to all hidden nodes and used to update their weights as follows. Error definition of backpropagation is made as follows. So the predicted value times 1 minus predicted value times difference between the predicted value and the actual value. Note that this is like an ordinary error multiplied by correction factor. In general, all of the models was assuming that this is the error, but right now there's kind of a little correction factor here, which is the underlined term here. For example, the error associated with my calculation N6 is as follows. My predicted value, 1 minus my predicted value, and then the difference between the actual value and the predicted value, just because for the first record, the actual value was like, which is 1, and my error is 0.123. So now the model updates the bias and the weights as follows. There's a term here called L. L is the learning rate. The learning rate is also developed by the model. Assuming a learning rate of 0.5, for example, the bias in node 6 is updated as follows. Initially, the bias 6 was set as negative 0.015, and now the updated version is the previous bias plus learning rate times the error I calculated a moment ago. Now, the bias in node 6 is updated from negative 0.015 to 0.047. So this is done in every node and updated until we get the best predictions. So this is the very simplified version of neural net theory. So last but not the least, some of the models we covered before, like linear regression and logistic regression, can be expressed as a special case of neural net. So that's why neural net is a very powerful method, just because it includes most of the models that we covered up to now. Okay, what are the advantages of neural networks? Neural networks have really great predictive ability, and it can capture complex relationships. So there is no need to specify a model. So you don't need to have a model in your mind. But there are disadvantages. These hidden layers are considered as a black box just because it does not assume any relationship between the predictor and outcome. There is no variable selection mechanism, so you have to exercise care in selecting the variables. We need a lot of data for training purposes. Extrapolation is also a serious danger, and this method has a very computational burden, so that's why it might be a little slow as the number of variables increases. This was a very brief introduction to neural nets. If you are interested in the details, please take a look at the references that I cited before. I hope you enjoyed this video and hope to see you in the next videos. Bye.